Testing, can you hear me? This video is now live. Okay, so I'm going to be studying discrete math again. Let me just change to full screen. All right, so last stream I was studying about counting. I learned about Pascal's triangle, combining outcomes and non-disjoint outcomes. This stream I'm going to start studying combinations and permutations. So, okay, let's start with the investigate. You have decided to decorate your magic wand with brands of different color tape. You have 10 different colors to choose from, and you will use 5 of them to create 5 different stripes of color. How many different wand designs are possible? And before going into combination and permutation, I think you should first know about factorials. So let's say you have 5 objects. Uh, what's happening here? Okay, let's say you have 5 objects. This A, B, C, D, and E. We need to fit them into 5 boxes. Do like this. I have 5 boxes. I need to fit these letters over here. So what are the total arrangements I can do? I can have A first, and then B, and then C, and then D, and then E. Or another arrangement I can have is that B first, or A, D, E, and C. Or I can have C, A, B, D, E. I can have many different arrangements basically. But you should notice that in this box, in the first box alone, I have 5 different possibilities. I have 5 different options to choose from. So A, B, C, D, and E. If I do choose one, then I have 4 different options for the second box. So for example, if I choose A, then for this box, I can choose either B, C, D, or E. If I choose B in the first box, then in the second box, I can choose A, C, D, C, D, E. If I choose, for example, E in the first box, I can choose A, B, C, D. Now, if I choose A for the first box, B for the second box, so I had 5 options at the start. When I choose one option, I have 4 options in the second box. When I choose a letter for the second box, I then have 3 options for the third box. So let's say I choose A and C. I choose A for the first, C for the second, then for the third, I have 3 options. D, B, E. If I choose E first and then C second, then I have 3 options: A, B, D. Similarly, so I start with 5 options, then I have 4 options, then 3, then 2. So if I choose B over here, then I have 2 options. If I choose D over here, then I have 1 option. If I choose A over here, then I have 2 options. If I choose B over here, then I have 1 option. So I have a choice of 5, then I have a choice of 4, then 3, 2, 1. So if I have 5 choices for the first one and 4 choices for the second one, then both of them together, a pair, would be 20 choices in total. So for each of the 5 choice, I have 4 choice. So for each of the 5 arrangement of the first one, I have 4 arrangements for the second one. So together there will be 20 different options for the first 2 boxes. So the first 2 boxes has has the first 2 boxes has 20 options in total. 20 options. 5 times 4. 20 options in total. The first 3 boxes, I should do like this. The first 3 boxes has 5 times 4 times 3 options in total. 5 times 4, 5 times 4 times 3. 60 options. So a total of 5 options together is 5 times 4 times 3 times 2 times 1 options in total. And there's a notation we use called the factorial. So this will have 5 times 4 times 3 times 2 times 1 is equal to 120 arrangements, I should say. Arrangements. Yeah. 20, 60, 120. Okay. Now, yeah. So we have a notion of 5 factorial, which is 5 times 5 times 4 times 3 times 2 times 1. In general, if I have n options, I want to know how many ways I can arrange n items. That would be n factorial. Which would be n times n minus 1 times n minus 2 all the way till 2 and then 1. Now the thing is, let's say instead of doing all 5 of them, I only did the first 3. So I have 5 items: A, B, C, D, and E. And how many ways can I put them in 3 boxes? Not 5, not all 5, just 3. Then I have 5 for the first one, 4 for the second one. After I chose this, I have 4 for the second one, and after I chose these two, I have 3 for this one. So in total, I have 5 times 4 times 3 arrangements. That's 60. 60 possible arrangements in this. Similarly, if I have A B C D E F G 1 2 3 4 5 6 7 options, and I chose 4 boxes. Then I have 7 options for the first one, A B C D E F G. After I choose one, and I then have 6 options for the second. After I choose this one, I then have 5 options for the third, and then I would have 4 options for the uh, fourth one. So in total, I would have 7 times 6 times 5 times 4 options in total. That's 7, 6, 5, 4, 840. 840. So 840 different options. This is called a permutation. Permutation. A permutation is basically, we write it like this. So NPK. And in the example above, I had 7 options and I wanted to arrange like four of those items. So in this case, it would be 7P4. So for 7 items, how many ways are there to choose 4? And in the previous option, I had 5P5, 5 options, and I'm arranging all 5 of them. But if I have 5 options and I was arranging 3, then it would be 5P5 permutation 3. Permutation this, like A, B, C, D, E. This is one permutation. B, C, A, D, E. This is a completely different permutation. If you switch the order, these are two, like the different arrangements are called different permutations. So the formula for permutation is, there are n factorial ways to arrange n items. Wait, no, this one. If you have n, if you have n items, there are n factorial ways to arrange them. But if you want a particular, if you have only if you have only k number of boxes, if you have k number of boxes, and you want to know how many ways are there to put n objects in k boxes, then we subtract, we divide this. So for example, for this, instead of, if we had 7 objects and we wanted to know how to put them in 7 objects, we would do 7 times 6 times 5, 4 times 5 times 4 times 3 times 2 times 1. So 7 factorial. If we only want 4 boxes, we just end at 4. We don't go all the way till 1. So normally for arranging n objects, we do n factorial. But if we are stopping at k, then we divide n minus k. So for the above, for 7p4, 7 factorial to arrange 7 objects. But if we only want 4 of them, the 3 times 2 times 1, the 3 times 2 times 1 over here needs to get removed. So 7 factorial ways of arranging 7 items. But we, since there are only 4 boxes, we are only stopping at 4. We only want this. So we are cancelling these 3 out. So these 3 needs to get cancelled out. So we need to arrange n factorial, but we are only considering the first k. So n minus k will get cancelled out. You decided to decorate your magic wand with bands of different color tape. You have 10 different colors to choose from. Okay, 10 different colors. A, B, C, D, E, F, G, H, I, J. I will name these colors with letters. And you will use five of them to create five different types of colors. Right. So I want one, two, three, four, five stripes. So how many ways can I have this in five stripes? It would be 10p5. So 10 factorial over 5 factorial. 10p. I thought they had a permutation calculator, right? 10p5. 30240. The product principle gives us a way to count the number of outcomes when each outcome is made by combining smaller pieces. A typical example of this is to count the number of three-letter words. Each outcome word we count is made up of combination of three smaller pieces, letters. Since there are 26 choices for each smaller piece, there are 26 times 26 times 26 possible outcomes. The product principle does not require that each piece that is being combined be chosen from a set of the same size. We will use this observation to create a standard way to count outcomes when the pieces are chosen from a fixed set, but without any piece to be used more than once. For example, we can ask how many three-letter words that there are that contain distinct letters. These arrangements are called permutations. We'll also consider another counting technique where we count combinations which are related but count something different. Yeah, we have another thing called combination. Suppose we have five items A, B, C, D, E. 1, 2, 3, 4, 5, 6. You have six items and you want to fit them in three boxes. How many ways to arrange them in three boxes? That would be n factorial and then divided by n minus k, which would be 6 factorial divided by 6 minus 3, 3 factorial. So you only want 6 times 5 times 4. The 3 times 2 times 1 that gets cancelled out. But here's the issue. We have the same object repeated twice. So how do you solve that problem? Because if these are different, if we have A, B, C, D, E, F, if we want to put them in three boxes, then A, B, F would be one permutation. A, F, B would be a different permutation. Similarly, for this first set over here, if I chose A first and then the first B on the second box and then the second B on this third box, that would be one permutation. And then if I chose this B over here and then this B over here, that would be a completely different permutation. So permutation treats all items as unique. We have combination on other hand that considers that some objects can be same. So in combination, these two are same. Uh, Different in permutation, same in combination. So what we do to count combination is we take the permutation, yeah, And then we divide the number of ways we can arrange the common letters. 2 factorial. Yeah, there are 2 factorial ways to arrange B1 and B2, which is just 2. So either B1 first and B2 second, or B2 first and B1 second. So we consider all different possible permutation, and we divide the number of ways uh, we can arrange the two of the same ones. That would be, yeah, yeah. This is not combination. Combination is something more. Combination is more like if we have something like A, A, B, B, A. So we divide the number of ways. So normally it's 6 factorial. 1, 2, 3, 4, 5, 6, yeah. But we divide the number of ways we can arrange the A's because we don't want to count the different arrangement of A's. And then we also divide the way we count the B. So that would be 6 factorial over 4 factorial times 2 factorial. So basically, if you have n items, uh, we want to arrange them. If k of them belong in one group and n minus k belong in another group, then we divide there are n factorial ways to arrange n items. There are n factorial ways to arrange n items, but if some of them were same, k a's and n minus k b's, if there are only two options we choose from and we want to find the number of different ways we can arrange them, then we divide the number of ways we can arrange the a's and also divide the number of ways we can arrange just the, like we can switch out just the b's. You have a bunch of poker chips that come in different colors: red, blue, green, purple, and yellow. How many two chip stacks are possible where the bottom chip must be red or blue? For example, the stack with a red chip on bottom and a green chip on top can be listed as RG. You have a two chip stack. I have a bunch of poker chips that come in 5 different colors: red, blue, green, purple, and yellow. So, red, blue, green, purple, and yellow. How many two chip stack are possible? So they mean like this. So 5 options for the first one and then 4 options for the second one. Or list all the possible two chips. I'm not doing that. What were the other questions? Okay, never mind this. A permutation is a possible arrangement of objects. For example, there are 6 permutations of the letter A, B, and C. A, B, C, A, C, B, B, A, C, B, C, A, C, B, A, C, A, B. In terms of a discrete structure, each permutation is really a sequence or tuple of a fixed length. You know that we have them all listed above. There are three choices for which letter we put first. Then two choices for which letter comes next, which leaves only one choice for the last letter. The multiplicative principle says that we multiply 3 times 2 times 1. Piece of notation is helpful here in factorial, which is a product of all positive integers less than or equal to n. So the number of permutations of 6 letters is 6 factorial. Sometimes we do not want to permute all the letters, numbers, elements we are given. How many four-letter words can you make from the letters A through G with no repeated letters? So A through G, A B C, A B C D E F G. A B C D E F G. 1, 2, 3, 4, 5, 6, 7. How many four-letter words? So 7 factorial. To arrange them, arrange these 7 letters in all the possible ways. So all the arrangements for these 7 letters, 7 factorial. And then we only want the first 4. So we are dividing it by 3 factorial, which would be 840. P and K is the number of K permutations of n elements. The number of ways to arrange K objects chosen from n distinct objects, which is n factorial divided by minus K factorial. Let's consider another way to count sequences. First count sets, then arrange them. Basketball team has 12 players. Assuming everyone can play every position, how many ways can you choose 5 players to be on the court at the same time? Wait. This question is actually too vague. Do we mean how many ways we select 5 players, or do we mean how many ways can we pick 5 players to fill the 5 positions? Because if we want to select, if we just want to select 5 out of 12 players, that is just like picking 5 out of 12 pizza toppings. We know that there are 12 choose 5 ways to do this. And from Pascal's triangle, we know that this is 792. Hold on. They have 12 players to choose from. So player 1, player 2, player 11, player 12. So 12 factorial over 12 minus 5 factorial. 95040. But the issue with this is if I have P1, P2, P3, P4, P5, that's one way of selecting 5 players. And then this is another way of selecting 5 players. But there is an issue. Like, should I not count them differently? Assuming everyone can play, how many ways can you choose 5 players to be on court at the same time? So this and this count as one, right? This and this don't count as different arrange. So the different arrangements within each five players doesn't count, right? So out of 12 players, there's 12 minus 5 factorial ways to choose 5 players. But then I also have to divide the number of ways I can arrange these 5 players. Yeah. So this is 12, choose 5. 792. Yeah, 792. So this is called combination 12, choose 5, or even 12, choose 7. So if I replace 5 with 7, like over here, this is 12 factorial, 7 factorial over 5 factorial. 7 plus 5 is 12. But so 12 choose 5, 12 choose 7, they are the same thing. The example above illustrates a second way to compute the number of k permutations of n elements. First select which k elements will be in the permutation, then count how many ways there are to arrange them. Once you have selected the set of k objects, we know there are k factorial ways to arrange them. But how do you select k objects from the n? You have n objects and you need to choose k of them. You can do that in n choose k ways. Using the multiplicative rule to combine the two steps, we get the formula for permutation. This is huge. We have a chosen formula for permutation already. Now substitute that in. Then we divide both sides by k factorial. We get the closed formula for n choose k. Another name for the correction of things that n choose k counts is combinations. We say that n choose k counts the number of k element combination of n elements. Sometimes we even use the notation C and K instead of NK. Perhaps combination is a misleading label. We don't mean it like a combination lock. Perhaps a better metaphor is a combination of flavors. We just need to decide which flavors to combine, not the order in which to combine them. Almost every source you look at about combination and permutation will make some variation of the following claim. Use a permutation when the order matters and use a combination when the order doesn't matter. What does this even mean? Suppose you're proposing a new lottery game. In the game, 5 numbered balls will be randomly shot out of the machine that holds balls numbered 1 to 50. If the player correctly picks the 5 numbers that come out, they win the jackpot. Of course, we want to know the odds of winning this lottery game, which requires us to know how many different outcomes there are. The balls flying the balls fly out of the machine randomly. So one result might be to get the balls 26, 5, 42, 17, 33. We're holding the ticket that had numbers 5, 17, 26, 33, 47. The acceptor have won most lottery games would say you have. Wait, why though? 5, 17, 26, 33. I think this is supposed to be 42, not 47. Since you have the same numbers just in a different order. In this sense, the order of the numbers does not matter. Better way to say this is that any order of the same numbers is considered the same outcome, and it is only and is counted only once. So really, we are counting the sets of 5 numbers, not the sequence of 5 numbers. Each outcome is a combination, so the number of outcomes should be 5. 52 choose 5. Okay, let's just go to the second one. Skittles come in 5 flavors. How many different handfuls of 8 Skittles are possible? So 5 flavors. How many different handfuls of 8 Skittles are possible? Suppose you have baked 8 identical cupcakes to give to your top 5 favorite discrete math teacher. How many ways can you distribute the cupcake? Why are the answers of the two counting questions above the same? So we have 5 flavors. 3, 4, 5. How many different handfuls of 8 Skittles are possible? Guessing. So the first Skittle can be any of the 5. Second Skittle can also be any of the 5. The third can also be any of the 5. So this 8 times. So 5 to the power of 8. Suppose you have a baked. Suppose you have baked 8 identical cups to give to your top 5 friends, top 5 favorite discrete math teachers. You baked 8 identical cupcakes to give to your top 5 favorite discrete math teachers. How many ways can you distribute the cupcakes? We know how to solve lots of types of counting problems now. If each outcome in the set of outcomes we are counting can be represented by a sequence, we count it as a permutation or use the product principle. We are counting outcomes for which we don't distinguish between arrangement of terms, then we can think of the outcome as a set and count it as a combination. However, sets never allow an element to be repeated. Each element is either in a set or not. So we have a glaring hole in our counting repertoire. What if we want to count outcomes that are collection of terms for which we do not distinguish between the order the terms appear in, but can contain terms more than once? In other words, how can we complete the following table? Distinguished arrangements, yes. Sequences, product rule, repeats, okay. No repeats. We use combination for this as well, right? Like how I explained last time. If 2 letters are there, one of them is repeated. A multiset is an unordered collection of elements, each of which can appear any number of times. The number of times an element appears is called its multiplicity. Multiplicity. Find a collection of identical objects, perhaps pennies or sugar cubes. Also, grab a few dividers, which could be toothpicks, matches, or pens. Line up the pennies in a single row. We will divide the row into some number of groups by placing the toothpicks in the spaces between the pennies. We will distinguish between which order the groups come in. For example, two different ways to divide 7 pennies into 4 groups would look like this. So 1, 1, 1, 2, 3, 2. So 7 pennies divided into 4 groups. This is one way. This is another way. 1, 2, 3, 1. We will allow for one or more groups to contain no pennies. By having two toothpicks next to each other, or before or after all of the pennies. Okay. Wait, so what they're saying is what they're saying is 1, 2, 3, 4, 5, 6, 7. You have a group over here. You have, say, 1, 2, 3 groups. But then the fourth group, it has no elements. 1, 2, 3, 4 groups. No, you have, how many toothpicks do you have? They're using 3 toothpicks, right? So 1, 2, 3, 4 groups. 1, 2, 3 groups. The fourth one has the fourth group has no elements. First group has no element, then second has 2, third has 5, the fourth has none. Or we can place them like this. First has 2, second has none, third has 5, and then fourth has none. By lining up the correct number of pennies and sticks, count the number of ways you can divide the rows of pennies into a given number of groups. If you want to divide a row of pennies into 4 groups, how many toothpicks will you need? 3. How many ways are there to separate a row of 3 pennies into 2 groups? There's only one way, right? Unless you're counting. So 1, 2, 3. So this is 3 groups. Did they say 3 groups? How many ways are there to separate a row of 3 pennies into 2 groups? So you have group 1, none of them. Group 2, all 3 of them. Group 1, one of them. Group 2, 2 of them. This is one way, and then this is another way. Oh, yeah. 3. Uh, so 1, 2, 3, 4. How many ways are there to separate a row of 4 pennies into 2 groups? So 1, 2, 3, 4. 4 pennies into 2 groups. No, this is wrong. So 1, 2, 3, 4, 5. 5 pennies into 2 groups, that would be 6. 3 pennies into 3 groups. The first group contains none, second group contains all 3, and then the third group contains none. 1, 2, 3. Then bring one back. 1, 2, 3. Bring one back. Hold on, this is 1, 2, 3, 4. This is 1, 2, 3, 4. This is 5, 6, and 7. This is 8 and 9. This is 10. So I would say 10. How many ways are there to separate a row of 4 pennies into 3 groups? Uh, okay. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14, and then 15. How many ways are there to separate 5 pennies into 3 groups? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and then 21. Make a conjecture about how you could separate a group of 7 pennies into 4 groups. So it's like 5 into 3 groups. 1, 2, 3, 4, 5, 6. So I did 6 plus 5 plus 4 plus 3 plus 1. And let me just check. 21. And then otherwise before this, it was 15. How many ways are there to separate rows of 3 pennies into 2 groups? 4. 4 pennies into 3 groups is 5. Then this is 6. Make a conjecture. So n pennies, if we have n pennies, 3 pennies in 2 groups, n pennies in 2 groups, we have n plus 1, n plus 1 ways of doing this. N pennies in 3 groups. We have n ISN to 1. What about n pennies in 4 groups? N pennies in 4 groups. So for 4 groups, we need 3 toothpicks. Let's put them all in the end. So 1, so for 5 pennies and 4 groups, this is no group, group of 5, no group, and then no group. So 1, this is one way to have groups. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 1, 2, 3, 4, 5. Wait, we are just doing this with 2 groups, right? With the 3 groups, right? Five pennies and 4 groups. You find the number of ways. So we have this. Find the number of ways to divide 5 pennies in 3 groups. And then we take one of the penny out. Like we shift this n9 one part here. And then we need to find the number of ways to arrange 4 pennies in in yeah, in a 4 group, in 3 groups. So one, one, two, three, 1, 2, 3. Right. So we do this process, but with 4 pennies. That's like, I think it's this. Consider the following counting problem. You have 7 cookies to give to 4 kids. How many ways can you do this? Take a moment to think about how you might solve this. You may assume that it is acceptable to give a kid no cookies. Also, the cookies are all identical and the order in which you give out the cookies does not matter. So giving the cookie to the second kid before the first kid does not count as a separate outcome as the other way. Before solving the problem, here is the wrong answer. You might guess that the answer should be 4 to the power of 7 because each of the 7 cookies of each of the because each of the for each of the 7 cookies there are 4 choices of kids to which you can give the cookie. This is reasonable but wrong. To see why, consider a few possible outcomes. We assign the first 6 cookies to kid A, the 7th cookie to kid B. Another outcome would be to assign the first cookie to kid B, the 6 remaining cookies to kid A. Both outcomes are included in the 4 to the power of 7 answer, but for our counting problem, the outcomes are really the same. Kid A gets 6 cookies and kid B gets 1 cookie. This would have been the correct answer if the cookies were all different, but they are not. What do outcomes actually look like? How can we represent them? One approach would be to write outcome as a string of 4 numbers like this, which represents the outcome in which the first kid gets 3 cookies, second and third kid each get 1, and the fourth kid gets 2. So 3 plus 1 plus 1 plus 2 is 7. Isn't that like asking how many sums of 7 there are? have seven cookies to give to four kids. How many ways can you do this? And that's like asking how many sums of seven there are, right? Uh, Represented this way, the order in which the cookies, in which the numbers occur matter. 1, 3, 1, 2 is a different outcome because the first kid gets one cookie instead of three. Each number in a string can be an integer between 0 and 7, but the answer is not 7 to the power of 4. We need the sum of the numbers to be 7. Another way we might represent outcomes is to write a string of 7 letters A, B, A, D, C, D. To represent the first cookie goes to kid A, the second cookie goes to kid B, third and fourth cookies go to kid A, and so on. In fact, this outcome is identical to the previous one. A gets 3 cookies, B and C get 1 each, and D gets 2. Each of the 7 letters in the string can be any of the 4 possible letters. But the number of such strings is not 4 to the power of 7 because here order does not matter. In fact, another way to write the same outcome is A, B, C, D, D. This will be the preferred representation of the outcome since we can write the letters in any order. You might as well write them in alphabetical order for the purpose of counting. Wouldn't it be 1, 2, 3, 4, 5, 6, 7? 7 factorial. 7 factorial ways to arrange this divided by 3 factorial. Uh, Actually, no, never mind. Yeah, I got confused. It is like writing a set, just that this multi-set can contain an element more than one time. So now we have two useful ways to think about the outcome. As a multi-set containing 7 elements, okay, as a string of 4 non-negative numbers with a sum of 7. Before we think about how to count the number of outcomes represented this way, we have a couple more examples of counting problems we can represent in these ways. 10 jelly beans from a bag that contains 6 flavors. Write down 3 possible outcomes. 10 jelly beans that contain 6. Okay. 1, 2, 3, 4, 5, 6. So this is a multi-set. Maybe show how many flavors there are for each jelly bean. Like which jelly bean is which flavor. Corresponding sequence of 6 numbers summing to 10 are. Okay, this is another way to present it. So there are. So out of the 6 flavors, we show how many jelly beans belong to that flavor. So 2 belongs to one flavor, 3 belongs to one, 4 belongs to one, 1 belongs to one. The sum is 10 because there are 10 jelly beans in total. Now let's return to the original problem distributing 4 cookies to 4 kids. We actually count the number of outcomes. When we were counting plain old sets, we saw that the numbers in Pascal's triangle gave us the count. In fact, we saw this was true because we could represent each set as a bit string. Whenever an element was in the set, we would denote that with a 1. If the element was not in the set, we would mark its absence with a 0. Given a multi-set such as A, B, C, D, D, You have a number of sequence representations as 3, 1, 1, 2. Well, instead of individual numbers, write each as a sequence of ones. This is slightly awkward since we are using commas. To make this clearer, let's switch to two different symbols. We call them sticks and stones. Stone, stick, stone, stick, stone, stick, stone, stone. Whatever two symbols we use, also call we might also see these called stars and bars or balls and pins. Use Pascal's triangle to count the number of ways to arrange them. The number of 10-bit strings of weight 3 is 120. In terms of cookies, we can view this sticks and stones diagram as saying after how many cookies you stop giving cookies to the first kid and start giving cookies to the second kid. Then after how many do we switch to the third kid and how many do we switch to the fourth? So 3, 1, 1, 2 means 3 to the first, and then 1 to the second, 1 to the third, and 2 to the fourth. While we're at it, we can also answer a related question. How many ways are there to distribute 7 cookies to 4 kids so that each kid gets at least 1 cookie? We can say that the corresponding sticks and stones, what can we say? What can you say about the corresponding sticks and stones charts? Charts must start and end with at least one stone. With at least one stone so that kids A and D get cookies. Okay, so they should start and end with a stone. They cannot have, okay, right. One way to ensure this is One way to ensure this is to place sticks only in the spaces between the stones. 7 stones, there are 6 spots between the stones. We must choose 3 of those 6 spots to fill with bars. There are 6 choose 3 ways to distribute 7 cookies to 4 kids, giving at least 1 cookie to each kid. Another way to approach this modified problem is to give each kid 1 cookie. Now the remaining 3 cookies can be distributed to 4 kids without restriction. So I have 3 stones and sticks for a total of 6 symbols, 3 of which must be bar. So again, we see that there are choose 3 ways to distribute the cookies. Your favorite mathematical ice cream parlor offers 10 flavors. How many mixtures could you create using 6? Not necessarily distinct scoops. The order you add the flavor does not matter, but you are allowed repeat. So one possible shake is triple chocolate, double cherry, and mint chocolate chip. Okay, so we have 6 flavors. We have 10 flavors and we are choosing 6. So flavor 1, 2. Yeah, I will mark them as if. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then I will have a divider, which I will represent as a 1, 1, 1. Or the sticks and stones representation was easier to visualize. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is it 6 flavors, right? 1, 2, 3, 4, 5, 6. And how many meshes could you create using exactly 6? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So one possible shake is triple chocolate, double cherry, and one mint chocolate chip. So the sum must be 6, right? Or here the sum must be 7. Wait, I need to see this. But you are allowed repeats. We get 6 scoops, each of which could be one of 10 possible flavors. Represent each scoop as a star. Think of going down the counter one flavor at a time. You see vanilla first, skip to the next chocolate. You say yes to chocolate 3 times, then switch to next flavor. There are 10 flavors to choose from, so we must switch from considering one flavor to the next 9 times. These are 9 bars. Now that we are confident we have the right number of sticks and stones, we answer the question simply. There are 6 stones and 9 bars. How do we have 9 bars? I don't understand. 6 stones and 9 bars. Okay, I think I know. I think I know. 1, 2, 3, 4. So 1, 2, 3, 4, 5, 6. 1, 1. Actually, yeah, let's use this. 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6. Okay, so group 1 is one flavor, group 2 is another flavor, group 3 is one flavor. So in total, there are 10 flavors. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So 10, 9, 8. Flavor 8 is chosen twice. Flavor 1 is chosen 0 times. Flavor 2 is chosen 0 times. The question is we have 1, 1, 0, 1, 1, 0, 1. How many ways we can arrange this? How many ways can we arrange these ones and zeros? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Wait, what? One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There are 9 bars and 6. 1, 2, 3, 4, 5, 6. Something is missing. This, 0, and then. And now it's 15. So 15 factorial of arranging this. But we have to divide the number of ways of arranging the zeros. 1, 2, 3, 4, 5, 6. And then 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is the final answer. Many of the counting problems in this section might at first appear to be examples of counting functions. After all, when we try to count the number of ways to distribute cookies to kids, you're assigning each cookie to a kid. It's just like you assign elements to a domain of a function to elements in the codomain. However, the number of ways to assign 7 cookies to 4 kids is 120, while the number of functions is 4 to the power of 7. What is going on here? When we count functions, we are counting the following 2 functions. For example, to be different. Uh, okay. But these two functions would correspond to the same cookie distribution. The point elements of the domain are distinguished, but cookies are indistinguishable. This is analogous to distinction between permutation and combination. All right. I will end the stream here then. And yeah, I'll continue. I think I will study calculus next stream. So, anyways, see you guys next time then. Bye.